In this lesson, we're going to be finding derivatives of functions that have logarithms and exponentials in them. And so I've got a bunch of new rules for you listed on the notes. And the idea is we're going to be using our product rule, quotient rule, and chain rule with these new derivatives. So let's just run through them very quickly. First one, derivative of e to the x is always e to the x. If you have another base, for example, let's say you have 2 to the x, then the derivative is natural log of 2 times 2 to the x. Okay, derivative of natural log of x is 1 over x. And if you have another base, let's say we have y equals log base 5 of x, the derivative of that is going to be 1 over ln 5 times x. All right, so let's just start doing some examples. In each of these problems, the very first thing you want to ask yourself is product rule, quotient rule, or chain rule. Is it a product, a quotient, or a composition? So 1a is actually a composition of functions. I would say that the inside function is the x squared, and then this e to the x squared can be written as e to the u. The outside function is e to the u. So my u prime would be 2x, and here's my new rule. The derivative of e to the u is e to the u. The chain rule says to find the derivative of a composition of functions, we take y prime times u prime. And then finally, we need to change those u's back into x's. If u is x squared, I'm going to write this derivative as 2x e to the x squared. Example B is also a chain rule problem. I have a function inside of a function. In this case, my inside function is the 3 minus x, and my outside function I can write as 5 to the u. Then my u prime would be negative 1, and my new rule says the derivative of 5 to the u is ln 5 times 5 to the u. Our chain rule says we take u prime times y prime. So I'm going to take negative 1 times ln 5 times 5 to the u. And then finally, I replace that u with an x, or in this case, with the 3 minus x. And so my answer is going to be negative natural log of 5 times 5 to the 3 minus x. Example C, this time we have a quotient. My numerator, my u, is e to the x. My denominator, my v, is x. So u prime is e to the x, and v prime is 1. And now because I have a quotient, I have to use my quotient rule. So the derivative is going to be u prime times v minus v prime times u all over v squared. Or we could write that as x e to the x minus e to the x divided by x squared. In example D, we have another example of a product. So I'm going to have to use the product rule. My u will be x to the third, and v is 10 to the 2x plus 1. That means u prime is 3x squared. And to find the v prime, I'm going to have to use the chain rule on this, as well as that new derivative rule for finding derivatives of exponential functions. Using the chain rule, the inside function is 2x plus 1, and the derivative of that inside function is 2. My outside function would be 10 to the u, and the derivative of 10 to the u is going to be natural log of 10 times 10 to the u. The chain rule says we multiply these derivatives together, so that means my v prime is going to be 2 times natural log of 10 times 10 to the u. Or if I replace that u with the 2x plus 1, then my v prime is going to be 2 natural log of 10 times 10 to the 2x plus 1. Finally, I'm going to plug this information into my product rule. The product rule says we take u prime times v So 3x squared times 10 to the 2x plus 1 plus v prime times u, that would be 2 natural log of 10 times 10 to the 2x plus 1 times x to the third. And that's it. There's not really much you can do to simplify this thing. There are no like terms at all. And so I would probably just leave my answer like this. If you want to, you could factor. You don't have to. But there is a greatest common factor of, let's see, well, you could take out a 10 to the 2x plus 1, and you could take out an x squared. And then you'd be left with a 3 plus 2 natural log of 10 times x. But again, it's not necessary to factor your answer. The important thing here is you have to use both the product rule and then you have to use the chain rule inside that product rule. Example E, g of x equals natural log of 2x minus 7. So I have to ask myself product rule, quotient rule, or chain rule. And this is a chain rule problem. The 2x minus 7 is actually inside that logarithm. It's not being multiplied. So the inside function is the 2x minus 7, and the outside function we could write as ln u. The derivative of 2x minus 7 is 2, and the new rule that we just learned, derivative of ln u would be 1 over u. And so the chain rule says the derivative of this function is u prime times y prime, or 2 over u. And if I write this with x's, I replace that u with the 2x minus 7, and there's my final answer, 2 over 2x minus 7. All right, let's get one more derivative example in, and then we'll do an application. But I think the idea here remains the same. You're using those same rules from the past. Product rule, quotient rule, chain rule. The difference is those 4 new derivatives that I gave you at the beginning of this discussion. So example F, this is a product. I see multiplication. The u is e to the 4x, and the v is log base 2 of x plus 5. Now to find the u prime and the v prime, in both of these, I have to use the chain rule. I'm going to try to do this without writing it out this time, without the u's and the y's. Okay, so for the u, e to the 4x, we have e to a power. The derivative of e to a power is e to the power. The chain rule says we have to multiply by the inside function, what was inside that power. And so in this case, we have to multiply by 4. Now I'm going to do the same kind of thing for my v prime. My outside function is the logarithm. My inside function is the x plus 5. The derivative of log base 2 of something would be 1 over natural log of 2 times that something. But then the chain rule says we have to multiply by the derivative of what was inside that logarithm, and the derivative of x plus 5 is 1. Now, using my product rule, I'm going to take u prime times v, so 4 e to the 4x times log base 2 of x plus 5 plus v prime times u, which I'm going to write as an e to the 4x over natural log of 2 times x plus 5. And that's my answer here. There really isn't any simplification we can do with that. That is our derivative. All right, let's get an example of an application in. And so that you might see the same kind of applications you've seen in the past. Things that have to do with marginal cost, marginal revenue, all of those things mean find derivatives. Or write equations of tangent lines. That means find derivative for the slope. I'm going to show you a new type of application. So this problem says a scientist has discovered that a population of bacteria will grow according to the following function, where t is measured in hours. How many bacteria will there be after 1 day? There is no calculus involved in this problem. 1 day would be 24 hours. And so if I want to figure out what the population is, I just have to plug 24 in for t. So I'll be computing 40 e to the 24 divided by 5. Now this is something that I'll have to put into my calculator. When I put this into my calculator, rounded to the nearest whole number, I got 4,860 bacteria. Now the second part of this problem is asking us, how fast is the bacteria growing after 1 day? This part of the problem is asking us for a rate of change. How is the population changing with time? That means this part of the problem is asking us to find a derivative. So we've got 40 e to the t divided by 5. I want to find the derivative of that. I'm going to use the chain rule. I don't have to use the product rule because 40 is a constant. So my inner function is the t divided by 5, and my outer function is the 40 e to the u. The derivative of t divided by 5 is 1/5, and the derivative of 40 e to the u is 40 e to the u. So the chain rule says that this derivative should be u prime times y prime. 40 times 1/5 is 8, and I'm going to change that u back to a t divided by 5. And then finally, if I want to know the rate of change after 1 day, I have to plug the 24 hours back into that derivative. I put this into my calculator and rounded to the nearest whole number. I got 972. And that would be bacteria per hour. So the population is growing at a rate of 972 bacteria per hour. That is it for Chapter 4. Let me know if you have any questions.